Welcome. In this session, we'll learn another class of discrete time systems. It's called a time invariant or shift invariant system. So what are time invariant or time variant systems? So a discrete time system is said to be time invariant. So if we say this is our system, so the system operates on this sequence x of n is said to be shift invariant for all n, for all inputs x of n and constant k, means for any value of x of n and constant k, if mathematically if this is true, means if we delay the input or time advance the input by some value k and the identical shift results in the output, then that system is said to be shift invariant or time invariant. So what's this saying? It's simply saying if the system input output relationship is this, now if the input to the system is x of n minus k, then if the identical shift results in the output, then that system is time invariant or time shift invariant. Otherwise, the system is time varying. Otherwise, if this is not true, the system is time varying. Right. Now, we can say it as time invariant system simply means we can define it like this also. Means no matter when you turn on the system for a given input, so no matter when you turn on this system, this output response will remain the same for a given input. So for a given input, the output is always the same, no matter when you apply this input. So by definition, this is the definition. Mathematically, you can write it like this. So if you delay the input by some amount, if the identical shift results in the output, then that system is referred as time invariant or shift invariant system. In other words, you can say no matter when you kick this system or turn on the system response for a given input will always be the same. Now to illustrate this further, as electrical engineers, let's borrow an example from continuous time system. Let's borrow a simple example from continuous time system. Let's suppose we have an RC network. To illustrate it, and let's suppose this is our source. So this is our source. Now, so this is our switch. Now see, I suppose our output is the voltage across this capacitor. See, so the output is the voltage across this capacitor. Now suppose the input to this network or the system is simply a DC signal. So suppose the input to this system is a DC signal, and let's suppose we turn on the system at t equal to 0. So we turn on this system at t equal to 0. So what will happen here? So we know this capacitor will start charging. We know this capacitor will simply start charging though. So this capacitor voltage will start rising. So this capacitor voltage will start rising. So it will start rising and go like this, and it will reach to this, and depending upon how much is the RC time constant of this system. So this is our VC. So this is our output voltage, and this is our input voltage. So we apply the DC voltage, and the capacitor starts charging. Now what we do? Now this we applied this voltage at t equal to 0. So we applied this voltage at t equal to 0. What we'll do next? We'll delay this input by some amount and apply this at suppose t equal to 5. Let's take an example. So this can be at t equal to 5. hours after this time, this can be after 5 minutes, 5 seconds, and so on. Now we apply the same input. The input is same, the input is not changing, but only we applied it at a different time instant. So let's see the output of this system for the same. We know capacitor will, if we neglected the effect of temperature and other environment conditions on this, we can see the output will remain the same. The output for this input will remain identical. That was true when we applied the same input at t equal to 0. So this will again start charging. And how much time it will take to reach this maximum value depending upon the RC time. So it is doing the same operation. So the operation remains the same, means it is doing the same charging operation here, no matter when you apply this system. So this is how we define a time invariant system. Means the output voltage will start rising no matter when you apply this. So if we neglect the environment effect here, we can say the output response of this system, RC system, is identical no matter when. So this is how we define a time invariant or shift invariant system. Mathematically, how do we check whether the system is time invariant or time vary? So how do we check whether the system is time invariant or time vary? So how do we do that? For this, we have 4 steps. Again, we have 4 steps to check whether the system is time varying or time shift invariant. Right, so the first step is determine the output, determine y of n, that's the output when input is x of n. And mostly this will be given, and this will be given, input output relationship will be given. Right. So second step is determine the output, delayed output, delayed output y of n by some constant k. So what we do, we delay this by k units of time, and let's call the resulting output. Let's call the resulting output we denote by resulting output is y of n minus k. So the third step is, so in the first step we determine y of n when the input is x of n, and this will be given. In the second step we delay the input. Whatever output is given to you, we delay that by k, means take replace n by n minus k. That's what we are doing. We're replacing n by n minus k in the step 2. Then in the third step, we determine the output corresponding corresponding to the input. So we determine the output let's call that output y of n comma k, n comma k is n comma k when the input is delayed input, when the input is x of n minus k. So you can say delayed or shifted input. So when the input is delayed or shifted, and we call that output, the resulting output, as y of n minus k. And how will we get this? Just having the input output relationship that we obtained in step 1. Now in the fourth step, what we do, we check whether y of n minus k that we obtained from second step is equal to y of n comma k. If these two are equal, then the system is time. So then the system is time. If not, then the system is time varying. To illustrate this, let's take a very simple example. Let's take the example. Suppose the system output is this, and time is x. So this is our output, input output relationship. So what's the first step to do? So what do we do in first step? We simply write the input output relationships, and mostly this will be given to you. So this is the output when the input is x of n, right? So then the second step, what we do, we replace n by n minus k. Wherever we have n, we replace that by n minus k. So replace n by n minus k. Let me use different basis for this. Suppose this is n minus k. Alright, so we replace n by n minus k. Wherever we have n, we replace the n by. That's the meaning of delaying the output. That's the meaning of delaying the output. Now, in the first step, what we do, we apply input. Means the input to the system is now delayed or shifted in, and we check the output, and let's call it y of n minus k. Now, having a look at this, we say, remember, time index is n, not k. The time index is n. So whatever is the input, we multiply that by the time variable, is the time instant. So from this, we can say the output will be simply n times the input. What's the input? X of n minus k. So simply what's this doing? This multiplying the sequence, means the x of n sequence by n. Whatever is the input, means whatever is the input, multiply it by the current time, means n. So you can see in the results in step 3 and 4 are not same. So y of n minus k is not equal to y of n comma k. So we can say this is a time varying system. This is a time varying system. So this is a time varying system. Now let me write some examples that you will solve at your own places. Let's suppose y of n is, so this is our system, and the output of the system is cos of x of n. So this is the first example that you will do yourself. Another example is a times x of n plus p. Similarly, third example is, let's suppose when the system operates on sequence x of n. Check whether these systems are time varying or time invariant. All right. So let's end it here. In the next session, we'll do how we represent any sequence in terms of delta function or simply unit sample sequence. All right, let's end it. And one more thing before I end this, remember, time invariant property is utilized by this convolution formula. So this is important for convolution. So please understand this. And before I discuss the other classes of this discrete time system, let's first derive the convolution sum. Means let's first learn what do we mean by convolution. Then we'll learn the other system properties of other systems. Stable system, what's an unstable system, what's a causal system, and what's an invertible system. That we shall learn later.